Hello. In this video I'm going to work through 8 sample exam questions and solutions for the no calculator free response portion of the AP Calculus BC exam, which is harder than the AB exam. Section 2 Part B, free response, again no calculator. You've got really 1 hour to do 4 questions on the exam, and you need to give explanation and show your work where requested. So besides solving the problems, I want to show you how to show your work and give explanation. That's part of what I'm going to do here. Again, like I said at the beginning, I'm going to work through 8 problems, so it's going to take a while to get through all these. But let's get going here. You can see the very first question is data-based. There's no formula for the function f or its derivative f prime. It says the second derivative exists and is continuous, so we want to make sure that we can get good approximations and good evaluations based on those assumptions, but you don't really need to worry about those assumptions too much. You might feel kind of scared when you look at this problem. Most people are used to dealing with problems where the function has some formula, but here we only have data. Okay, if you encounter a question like this, just take a breath and say to yourself, okay, I need to use more abstract formulas or principles to help me solve this. I need, in part A, to approximate the second derivative of this function at x equals 2. I know the derivative is defined in terms of a difference quotient, a limit of difference quotients, and I also know the second derivative is the derivative of the first derivative. So from a theoretical abstract standpoint, I could certainly write f double prime of 2, and sorry this pen doesn't always work so well, I'll do my best. F double prime at 2 is a limit. Not that we're going to calculate a limit here, but from the abstract principle, I know that's the definition of a derivative, typically written as h goes to 0 of something called a difference quotient, which is certainly a quotient, and the numerator is certainly a difference. It's a difference of function values. Now remember, I'm after f double prime here, the derivative of the derivative, so the difference up here is a difference of derivative values, not original function values. F prime of 2 plus h, 2 is playing the role of x here, that's a 2. 2 plus h minus f prime of 2, all divided by h. So there's the abstract formula, which you can certainly show as part of your work. But how in the world can we use this when we only have data? Well, we can think about the fact that if I let h be close to 0, but not equal to 0, and get rid of this limit sign, it should be, at least if f prime is continuous, which it would be since f double prime is continuous, a good approximation to the derivative. Based on the fact that these x values are all 1 unit apart, it seems that the best choices I can make for h are h equals 1 and h equals negative 1. And that's what I'm going to do. And it should make some intuitive sense that if I average those slopes of secant lines after doing the calculation, it's probably the best possible answer. So that's what we're going to do. Start by letting h equal to 1. And what will this difference quotient equal when h equals 1? Plug in h equals 1 right there and there. You can't plug in 0 because you'd be dividing by 0. You can't plug in 0.1 because, well, the table doesn't have enough data. 2 plus h would be 2 plus 1 is 3, minus f prime of 2, divided by h is 1. 3 minus 2 is really the change in x here. Well, now look at the table. F prime of 3 is right here, it's 13. F prime of 2, it's right there, it's 16. So this is 13 minus 16, all divided by 1. It's probably a good idea to show that. 13 minus 16 divided by 1, that is negative 3. Again, sorry about my pen, it just doesn't always work the greatest. I'll do my best. Well, what about if h is negative 1? Again, go back up here, ignore the limit sign. We're not actually taking the limit. The limit, we're plugging in values of h close to 0, but not equal to 0. And again, based on the x values being 1 unit apart, we're going to pick 1 and negative 1. All right, so we get f prime of 2 plus h, 2 plus negative 1 is 1. Minus f prime of 2 divided by h, which is negative 1 in this case. Careful. Okay, h is negative 1. F prime of 1 is right there. So this is 18 minus 16 divided by negative 1. 2 divided by negative 1 is negative 2. Okay? You can also think of that as 16 minus 18 divided by positive 1 as well, but if you're going to use this formula without the limit sign, and if h is negative 1, then technically you are thinking about it this way. So now just average these two things, and your best approximation for f double prime of 2, average of negative 3 and negative 2 is negative 2.5. Negative 3 plus negative 2 is negative 5. Divided by 2 is negative 5 halves, or negative 2.5 is your best approximation from these data of f double prime of 2. So we've done part A. All right, on to part B. This one looks harder. Evaluate that integral. What in the world? Not only do we not have a formula for f or f prime, we've also got an x squared inside there and a 3x out there. And then in C, we've got to evaluate this integral of x times f double prime. What in the world? How can we possibly do these things? Take a breath. If this were a 2x there instead of a 3x, if that were a 2 instead of a 3, with enough thought, I hope, and experience, you would realize that if you did a substitution, u equals x squared, then u prime would be 2x. du, if you like using the du, would be 2x dx. It's a 3 there instead of a 2, but I can account for that. I could say, think of 3 as 2 times 3 halves, and factor out a 3 halves. 3 halves times the integral from 0 to 2 of 2x f prime of x squared. It's very frustrating for me that this pen does this, but we have to live with it. Okay, so yeah, now try this substitution. Sometimes you just have to try something and see if it works. Try letting u equal x squared. So du, if you like using the du notation, would be u prime dx. U prime is 2x, that's the derivative of x squared with respect to x, so I get 2x dx. And so the 2x dx can be replaced by a du, and the x squared can be replaced by a u as well. So I get 3 halves times the integral from, well, let's not worry about the limits of integration at the moment. 3 halves f integral of f prime of u du. But if these are going to be equal as definite integrals, I do now need to change the limits of integration. So I'm using properties that you've used with particular examples before, but now I'm applying them in the abstract. Use this equation. When x is 0, u is 0 squared is still 0. And when x is 2, u is 2 squared, which is full. And if nothing else, at least we got a simpler looking integral. But there's still something else we need here to help us finish this problem. You could perhaps think in terms of Riemann sums, but you don't need to. And in fact, it's better to realize you can use the fundamental theorem of calculus here. We're integrating a derivative from 0 to 4 in this case. That means I need an antiderivative. I need to plug 4 in there, subtract what I get when I plug in 0. Fundamental theorem of calculus. This is going to be 3 halves times, in parentheses, f, because f is an antiderivative of f prime, of 4 minus f of 0. And now we can definitely finish this problem. 3 halves, f of 4, where is that? That's 14. F of 0 is 2. 3 halves times 14 minus 2 is 3 halves times 12 is 18. There we go, we did it. Okay? It can be surprising what you can do if you know your stuff. If you have practiced stuff enough and maybe memorized to remember the idea of u substitution even in an abstract situation in the fundamental theorem of calculus. 18 is the answer. All right, on to part C. Integrate from 1 to 3 x times f double prime of x. Substitution doesn't seem so helpful here. What would u be? X? Well, You could let u equal x, but it doesn't really help. You just get an equivalent integral. What's the other main rule of integration that you've learned besides substitution? And when I say main, I don't mean specialized like method of partial fractions or something. I mean integration by parts. What does the integration by parts formula say? Well, some books write it as the integral of u v prime dx, say, with respect to x, is u and v are functions of x, would be u times v minus the integral of v times u prime. Some books write it that way. Some books write it in, I think, a bit better notation. U dv, though maybe more confusing, is u times v minus the integral of v du. And again, everything depends on x. I'm just not putting the x in there explicitly. In effect, when you do integration by parts, you are swapping where the derivative goes. Let me show you how that works out in this problem here. If I let u equal x and let dv be f double prime of x dx, or if you prefer, you could say v prime is f double prime. I can write that over here. V prime is f double prime. When you think about this formula, you are swapping the derivative symbol from being on the v to being on the u. Got a u prime there, you got a du there. And hey, u has a nice derivative. It's a constant function. U prime is 1. That might make the integral simpler. And in fact, it'll also relate it to f prime. And then with the FTC, the fundamental theorem of calculus, I'll be able to use data about f. Yeah, this is the way to go. U times v, well, what is v? If v prime is f double prime, then v is f prime. Plus c? Do you need to add on plus c? No, you don't have to, because any antiderivative works. You can take c to be 0. So think about this formula. U times v is x times f prime. So I'd have to add x times f prime of x, evaluated from 1 to 3. When you do integration by parts, you leave the limits of integration the same. When you do substitution, you have to change them. Minus the integral of v times u prime. V is f prime. U prime is 1. U prime is 1. Or du is dx. V again is f prime, so this is the integral of f prime. Oh, sorry. That's really frustrating. This is an f prime of x. I hope you liked the video enough to stay with me in spite of this. So, we'll need the FTC, fundamental theorem of calculus there. This will equal f of 3 minus f of 1. And what does this equal? Well, you need to understand this notation. It means plug 3 in for x and then subtract what you get when you plug 1 in for x, when you draw this vertical line here. So we get 3 times f prime of 3 minus 1 times f prime of 1, which of course is just f prime of 1, minus, careful about signs, this is an f prime in there that's going to be f of 3 minus f of 1. Fundamental theorem of calculus. That's an f prime of x is what we are integrating there. Now plug the numbers in. What numbers? F of 3, f of 1, those two numbers, f prime of 3 and f prime of 1 as well. These two numbers. So it looks like we're going to get 3 times f prime of 3 is 13, f prime of 1 is 18, minus, you can distribute the minus sign through if you like, but I'll just do it like this. F of 3 is 12, f of 1 is 15. So really subtracting negative 3, which really means we're adding 3. This is 39 there. 39 minus 18 is 21. 21 plus 3 is 24. The answer is 24. Okay? I think this problem is kind of fun, but it certainly is scary when you first look at it. Okay? You really need to know your stuff, but once you understand your stuff, it's actually kind of fun. All right, let's go on to the next problem. The first of 8, I do have timestamps for the videos if you want to jump to different problems. Number 2, a population is modeled. Okay, so this is a population model by a function p. Now they didn't put an of t in there, but it's understood that p depends on t. It could have been written as p of t, and in fact that's hinted at down here as well. That satisfies a differential equation. What differential equation? This one right here, where t is time in years, and this is the derivative dp dt, the rate of change of p with respect to t. T is time in years, and k is the constant of proportionality. Not saying anything about whether this is a good model, we're just using it. When t equals 0, the population is 150. In other words, p of 0 is 150. Now I'm thinking about function notation here. I could have written it there as well. And that's emphasized in part A. Find p of t in terms of t and k. How? You actually could try to get away with guessing, and some people are quick enough to be able to guess this kind of thing, but most people are not. So what we need to do is we need to solve the differential equation. And for this kind of equation, the standard method is to try to get all the p's on one side and all the t's on the other. There's a dp, which does involve a p on the left side, and an 800 minus p on the right side. Let me get the p's on the left side. Where are the t's? Well, there's only a dt, which does still involve a t. How do I get that to the other side? I pretend this is a fraction. Now, you probably had a teacher say, hey, it's not a fraction. And I'm saying that too, it's not a fraction, at least when you're first learning calculus. There's actually some more advanced kinds of calculus you can do where you actually can pretend it's a fraction, a ratio of what are called infinitesimals, but that's way beyond the scope of a standard calculus or AP calculus class. So we pretend it's a fraction, and it turns out we get the right answer. So it's justified, you know, the ends justifies the means. We get the right answer in the end. So I pretend dt is a number I can multiply both sides by to cancel with the dt on the left, and I'll get a dt on the right. And bring the p term, this factor here, 800 minus p, over to the left by dividing both sides by it, and it will cancel on the right. What should I do about the k? Should it be on the right or should it be on the left? Or maybe it doesn't matter. Well, the answer is it really doesn't matter, though I find it easier to keep it on the right. That is an equivalent way to write the differential equation. Okay? And when you see something like this, again, dp and dt are sometimes called infinitesimals. They're also sometimes called differentials. When you see something like this, you should start feeling an uncontrollable urge to integrate both sides of that equation. Okay, and you should go ahead and do the integral. The right side is easy. K is a constant. This just gives kt plus an arbitrary constant. K is a fixed constant. C is arbitrary. Turns out I'm going to call it C1 because I'm going to have some other C's come into play. Now, if you're good at this, you can get away without the subscripts, but probably when you're first learning or first practicing and trying to pass the exam, it's probably good to label it, say, C1. What is the left side? That's not too hard to do either. Sometimes in these problems, you might have a more complicated differential equation involving what's called a logistic model, and maybe have an extra factor of p in here and also an extra factor of p down here, and you'd have to use partial fractions. It's doable, but harder. This one can be done. You know the integral of 1 over x dx is natural log of the absolute value of x plus c. We don't have a 1 over p, we've got a 1 over 800 minus p, but essentially a substitution, u equals 800 minus p would help us solve this. If u is 800 minus p, let me just do a side calculation here, then du would be negative dp. So we could do that substitution and integrate 1 over u, but we would pay for it, so to speak, with the minus sign. And you can put that minus sign out in front, negative natural log of the absolute value of 800 minus p in here. Should I put a plus c, like a plus c2? Actually, here you don't have to, because you could just imagine it's been subtracted from both sides and it's been absorbed into the c1. It's good enough just to have it on the right side. Now solve this equation for p. We're after p is a function of t and k. In terms of t and k, it's really a function of t. K is fixed. Got a log I probably need to exponentiate, but there's a minus sign there. Is that going to cause me trouble? Well, no, not if you know how to deal with it. You could certainly bring it into the exponent of 800 minus p. I find it easier to think of it as multiplying both sides by -1 and get natural log of the absolute value of 800 minus p equals negative kt. You do need the negative sign there. That's essential. Minus c1, well, just call it plus c2 now, where c2 is negative c1. But these are arbitrary constants anyway, so it doesn't matter what you call them, and you might as well use a plus sign. But here you've got to have the minus sign. Exponentiate to get rid of the natural log, using the fact that e to the x and natural log of x are inverse functions. That gives you the absolute value of 800 minus p is e raised to this entire power there. But wait a minute. E to this plus that, by properties of exponents, is the product e to the c2 times e to the negative kt. And e to the c2 is sort of like another arbitrary constant. Call it c3. But c3 is not really arbitrary in the usual sense because it's a power of e. It would have to be positive. However, this is very pseudo-justification here. If I get rid of the absolute value signs, then you could say call it c4, where c4 is plus or minus c3, say. It's not a rigorous justification. It's hand-wavy. It works in the end. You can get rid of the absolute value sign. C4 essentially is plus or minus C3. That actually does exclude the case where C4 is 0 because, again, e to a power can never be 0 either. I'll just go ahead and leave it like this. Maybe we want to just now call this C. Our goal is to solve for P. Okay, let's leave it as a C4. Let's add P to both sides and subtract C4 e to the negative KT from both sides. And then negative C4 e to the negative KT, I could call plus C5 e to the negative KT, but I think I'll dispense with the subscripts at that point. If you do that, the P's cancel, and here these two cancel. You've solved for P. P of T, let me write it up here. P of T, and you could write function notation here, is, what would it be? I'd have the P on this side. It equals 800 minus that, which I can think of as 800 plus, I'll just call it C. C e to the negative KT, where C is an arbitrary constant. We're actually not quite done with part A yet. I want to figure out what the arbitrary constant is, and that's based on this initial condition. At time 0, the population is 150. So plug that in. 150 is P of 0. 800 e to the 0 is 1. C times 1 is C. So C actually does end up being a negative number if I write it like this. It's 150 minus 800 is negative 650. So maybe it would have been better to write it as minus C. But it doesn't matter. As long as your final answer is right, it doesn't matter. So the final answer, hopefully my pen is going to work okay. P of T, let's try it out here. P of T is 800 minus 650. 650 e to the negative KT is what I'm trying to write here. Okay, let's put it over here. P of T is 800 minus 650 e to the negative KT. Now we've got P in terms of K and T. I'm emphasizing that T is the variable by putting it in there. K is a constant. That's how to write the answer to part A. Part B and C are quicker. Part B says if P of 5 is 300, find K. We're going to need a logarithm. We will, But wait a minute, this is a no calculator portion. Well, just write your answer in terms of the logarithm. Use this condition to find k. So 300 is p of 5. So that's 800 minus 650. E to the plug in t equals 5, you get negative 5k. Solve that for k. Your answer will involve a logarithm, and we will not be able to approximate it because we don't have a calculator. I could subtract 800 from both sides to get a negative 500 on the left. Divide both sides by negative 650. The minus signs would cancel. I get e to the negative 5k is 650, 500 over 650, excuse me. 500 over 650, which simplifies to, let's see, 5/65, which is which is 10/13. 10/13. Hopefully I didn't make a mistake with my arithmetic there. And then take the log of both sides and then divide both sides by negative 5. K is going to be negative 1/5 the natural log of 10/13 times the natural log of 10/13, which is actually a positive number because natural log of a number between 0 and 1 is negative. So we get the product of two negatives. This is actually a positive number. I did calculate it before I made this video. It was somewhere in the ballpark of 0.05 or 0.06 or 0.07. I don't remember exactly. Somewhere in that ballpark. But we don't need it. Wait a minute. Wouldn't we need it for part C to find that limit? No. You don't need to know what k is other than the fact that it's positive. To find the limit of this function as t goes to infinity, if k is positive, then negative k is negative, and t is going to plus infinity. So you got e to a power that's getting more and more negative, unboundedly so. This does go to 0 as t goes to infinity. And that means this limit is 800 minus 650 times 0, which is 800 minus 0, which is 800. Say the whole thing here goes to 800 minus 650 times 0 is 800 as t goes to infinity. Okay, so again, we're showing work. This is free response. This is fine kind of work. We haven't been asked to explain anything yet, but that's not being ruled out. Okay, kind of messy, but I hope you've tracked along with me. Next question here. I'm going to quick get a drink. All right, pull up the next question. Oh boy, Maclaurin series. Yikes. People always find this difficult. Also known as Taylor series, centered at x equals 0. Taylor series and Maclaurin series are the same thing when we are centering on 0, which is the usual case. When we're centering somewhere else other than 0, then we always call it a Taylor series. So Maclaurin only gets credit for Taylor series at 0. I think I read about the history of it, but I don't really remember the details. Maclaurin series for f of x is given by that formula. For what values of x does this converge? Let g prime be this. What's the Maclaurin series for g prime? Is it a familiar function? Evidently it is. Ultimately, we find a formula for g in terms of familiar function without a series. So you got to know some facts here. As far as part A goes, you got to know how to decide whether a power series like this converges or not. And the standard thing to use here is the ratio test, especially when you've got factorials involved. We want to look at the limit as n goes to infinity of the general term. Let me call this the general term. Let me call it an. The absolute value of the general term an plus 1 divided by the absolute value of an. This limit is what's part of the ratio test. if this limit exists, and it actually doesn't always exist, there are some really tricky examples where it doesn't exist, but you still might be able to conclude something. If it does exist, and in these examples it definitely does, and is less than 1, it means the series converges. If it's greater than 1, it means the series diverges. And if it equals 1, then there's no conclusion. However, what's x? Well, x can be anything, so the answer might depend on x. In general, we get an interval of convergence. Maybe a very limited set of x values where this will converge. However, intuitively, because we're dividing by factorials, intuitively, these terms are going to go to 0 very fast, and that means the series likely will converge no matter what x is. Probably the answer is all x. Well, let's go ahead and see what happens. So limit sign, n goes to infinity. an plus 1 in absolute value, I can get rid of the negative 1 to the n power. I do need the absolute value around the x to the 2n, or if you prefer, the absolute value of x to the 2n, but replace n with n plus 1, so I really get 2n plus 2, right? Because 2 times n plus 1 is 2n plus 2. And, well, factorials are positive. I don't need absolute value signs down here. Replace n with n plus 1, I'm actually going to get 2n plus 4 factorial. Right? When I replace n with n plus 1 and distribute the 2 through the parentheses, just like here, I get 2n plus 2 plus another 2 is 2n plus 4. Dividing by the absolute value of an is the same as multiplying times its reciprocal, so essentially you get the same fraction flipped and adjusted with the exponent there and what is being factorialized there. That was a word that I'd never said before, factorialized. It's probably not a word. N gives you exactly this, flipped. Get rid of the minus sign because we're taking absolute values. But we do need the absolute value sign in general around the x. Because x could be negative. And you do want to think about this as a positive quantity, so you need absolute value signs there. Looks kind of scary, but looks are deceiving. This is actually pretty easy to deal with right now. This is the same as 2n plus 4 times 2n plus 3 times 2n plus 2 times 2n plus 1, etc. But hey, 2n plus 2 times 2n plus 1 plus 2n, etc. is the same as 2n plus 2 factorial. So this cancels with this. And raising this to that power is the same as this. Yeah. This. And that means this cancels with that. And you're left with the absolute value of x squared over this. And actually don't need absolute value signs anymore. This is an n here, not an h, by the way, again. N is going to infinity. Because when you square a real number, you never get a negative number. So I can just write this. But doesn't that seem difficult? What in the world, how in the world can we compute that limit? Well, remember, I can think of x as fixed. I'm letting n go to infinity and thinking of x as fixed. Now, x could be a humongous number, like 10 to the 100th power or something. And then 10 squared would be 10 to the 200th power. Doesn't matter. It's still fixed. I'm still dividing by numbers that are getting arbitrarily large. Way bigger than 10 to the 200, 10 to the million, 10 to the billion, 10 to the Google power with the Google factorials. Yeah, you get the idea. This limit is 0, no matter what x is. And that's less than 1 for all x. That would be good to add in your explanation. And therefore, the answer to A is it converges for all x, because the limit in the ratio test is less than 1. It converges for all x. That is the interval of convergence. The interval from minus infinity to infinity, or fancy looking R, double struck R if you prefer for the real number system, that is the answer to A. Right? B. G prime of x is defined to be this, where G is some unknown function. So what do I do to find a formula for G prime? It's Maclaurin series in particular. I just use the Maclaurin series for f. To save time, I'll just do this. So you're going to multiply each term by negative x squared, and then add 1 at the beginning. This times negative x squared is minus x squared over 2 factorial. This term times negative x squared is plus x to the 4th over 4 factorial. This one times negative x squared is minus x to the 6th over 6 factorial. And this should look familiar. That's the first, I guess I did 4 non-zero terms when we were only after 3, but I did 4. I am after the general term. It's analogous to this except replace, well, the power needs to match what's being factorialized. There's the second time I used the word factorialized, which again is probably not a word. And we got a negative 1, the signs are oscillating. Write it like this, that makes those two numbers match. Is the power of negative 1 going to be n or something else? Well, it starts positive when n is 0, then it's negative when n is not 2 but 1, because 2 is 2 times 1. 2 factorial is 2 times 1 factorial. Positive when n is 2, the 4 is 2 times 2. So it's positive when n is even, negative when n is odd, and so it does look like this will work. It doesn't contradict the fact that we multiply this whole thing by negative 1. If I had written, I could have written the general term with a 2n plus 2 there and a 2n plus 2 factorial there, and then we would have had negative 1 to the, say, n plus 1 power instead. Just check based on the pattern. That's the answer to A, or B, excuse me. Part C, write G prime of x in terms of a familiar function. You need some knowledge here, something you've remembered or memorized. And the thing to remember is this is this Taylor series, or Maclaurin series, for the cosine function. That does equal cosine of x no matter what x is, for all x. The series not only converges for all x, but it actually equals the cosine function. To show it equals the cosine function, you need more than the ratio test. The ratio test only converged for all x. It doesn't confirm that it converges to cosine of x. You need what's called an error-bound theorem for the Taylor series, which we're actually going to do a problem about here soon. But you can just use this fact. Now write f of x in terms of that same familiar function. You've got to use this equation. Solve for f of x. G prime of x is the cosine function. Solve this for f of x. You're going to get, well, first subtract 1 from both sides, and then divide both sides by negative x squared. F of x is going to be, careful here, it's really a piecewise function. It's going to be 1 minus cosine of x divided by x squared, as long as I don't divide by 0, if x is non-zero. X is non-zero. When you solve this for f of x, subtract 1, you get g prime of x minus 1, which is cosine of x minus 1, divided by negative x squared, but then you can switch around the top and get rid of the negative sign on the bottom, and you can write it as 1 minus cosine of x over x squared. And I forget how to get rid of this thing. No, not that. Okay. But is it defined at x equals 0? It is. And for full credit, you need to know this. How do you know, and what does it equal? Go back to the original series. That's the f of x. That is defined at x equals 0. It's 1 over 2 factorial, 1/2. What's going on here? This this expression right there as a function of x is not defined when x is 0. However, it does have a limit as x approaches 0. And you might want to pause the video and use L'Hopital's rule as another little extra exercise to confirm that the limit of this expression as x goes to 0 is 1/2. This function, if you thought of it as being defined for all x, including x equals 0, to be maybe something else other than 1/2, would have a removable discontinuity at x equals 0. And if you redefine it to equal 1/2 at when x is 0, then it would fill in the discontinuity. Part D, given that g of 0 is 4, write g of x in terms of a familiar function without series. Well, g prime is cosine of x. G prime of x is cos x. So to find g of x, I need to integrate. That's an x there. Maybe I should somehow mark this as the spot where things go bad. It's a cosine of x. So g should be the integral of cosine. Sine plus c? Yeah, plus c. And you want to choose c so that g of 0 is 4. Now sine of 0 is 0, so the answer should be sine of x plus 4. G of x, where should I write it? G of x is going to be sine of x and then plus 4. Don't put the 4 inside. It might be safer to write it as 4 plus sine x if you don't bother putting parentheses around the x. The sine function at 0 is 0. I need to do a vertical translation of that graph so that g of 0 is 4. It's got a vertical intercept of 4. That would be the answer to part D. Oh, okay. Number 3. On to number 4. These are not easy problems. You gotta really know your stuff. Gotta have some things memorized, including on this problem too. So we've got a graph of a polar curve, r equals 2 minus cos theta, as theta goes from 0 to 2 pi in this picture. You graph polar equations by letting the angle theta vary and then plotting a point at r units from the origin, at least when r is positive. It gets a little trickier when r can become negative. But this function will never be negative. 2 minus cos theta will never be less than 1, in fact. So and when the angle is 0, 2 minus cosine of 0 is 2 minus 1 is 1. That's the distance to the origin. What about when the angle is 90 degrees? Pi over 2 radians. It looks like it should be 2 units from the origin. Is it? 2 minus cosine of pi over 2. Cos pi over 2 is 0. 2 minus 0 is 2. Yeah, that's 2 units from the origin. So you get this kind of funny looking almost circle, sometimes called a cardioid because it kind of can look like a heart sometimes, although this is not a very strong looking sideways heart. Find the area of the region. You need to know a formula. The area of such a region is, it's going to be an integral, but what's the integrand? It's 1/2 times the function squared. Think of this as an f of theta. 1/2 times the integral of f of theta squared. I put the half on the outside. I could have put it on the inside. As theta goes, in this case, from 0 to 2 pi. So I need to square 2 minus cos theta. FOIL it. You get 1/2 times the integral from 0 to 2 pi of 2 times 2 is 4. For the first times first. The outside times outside terms, if I imagine another factor of 2 minus cosine theta, would be 2 times negative cos theta, and then another negative cos theta times 2. Minus 4 cos theta is what we get. And then last times last is negative cos theta times negative cos theta is positive cos squared theta. To do this integral, those two are easier to integrate. This one's a bit harder. It's it's good to memorize a certain trig identity here. I use the fact that this I know is 1/2 plus 1/2 cos 2 theta. That's just something I've memorized, and I think it, especially for these kinds of problems, that is good to memorize. To save time, to finish this, you can fill in more details if you like. I know from experience that when you integrate these expressions, the ones that involve the cos theta and the cos 2 theta become 0 when your integral is from 0 to 2 pi. Because cos 2 pi, cos 4 pi are all equal to cos of 0, which is 1, everything cancels. The only thing that's going to give you non-zero answer for the integral portion comes from this 1/2 right here, this 4 right here, and the 1/2 out in front being multiplied times those. Ultimately, if you integrate, well, 4 plus 1/2 is 9/2. 1/2 times 9/2 is 9/4. You're going to ultimately integrate 9/4 from 0 to 2 pi. You're ultimately going to get 9/4 times 2 pi minus 0. The final answer is 9 pi over 2 for the area of this cardioid-like shape. And what is that approximately? Somewhere in the ballpark of 15. Okay? And if you count boxes here, which each have an area of 1, kind of all, you should get close to 15. You can also integrate from 0 to pi and double the answer, but this seems fine to me. That's part A. Part B, write expressions for dx d theta and dy d theta in terms of theta. That might seem hard. Find x and y in terms of theta first, though. Using your equations that convert polar coordinates back to rectangular. X equals r cos theta. Y equals r sine theta. R is, for points on this curve, it equals this. Replace r with f of theta. So we get 2 minus cos theta times cos theta. And we get 2 minus cos theta times sine theta. For y. If I'm going to differentiate this, it's probably best to multiply these through. So, dx d theta, the derivative of x with respect to theta, which does give you the rate of change of the x coordinate of the point as theta varies. Just differentiate this after I multiplied the cos through. Derivative of 2 cos theta is negative 2 sine theta. And then we also differentiate negative cos squared theta. So that derivative with the chain rule, negative cos squared theta is what we're differentiating. And the negative sign is out in front of it. It's not inside, so it doesn't go away because of squaring. Bring down the 2. I have minus 2 cos theta times the derivative of cos theta is another negative sine theta. Looks like it should be 2 cos theta sine theta. If I did not make a mistake. And if I did make a mistake, I'll put a note about it on the video. I do make mistakes. So that looks like it's dx d theta, dy d theta. Differentiate this with respect to theta. The derivative of 2 sine theta is 2 cos theta. And then the derivative of minus cos theta sine theta, I can use the product rule for that. Careful about the minus sign. Derivative, let me say, derivative of negative cos theta is positive sine theta. So times another sign, that gives me plus sine squared theta. And then, so that was the derivative of the first function times the second. Plus the first function, which is negative cos theta, times the derivative of the second. You're going to get minus cos squared theta. And there's a trigonometric identity that would allow you to change that. It does not equal 1 because of the minus sign there. But this is fine for the answer. to B. Now C. Find dy dx as a function of theta. What? How do you do that? Well, there's a formula. I'll put the formula up here. We in part D will also need to plug theta equals pi over 2 into that to get a slope of a tangent line in part D. Slope of this line here, in fact, this tangent line at this point is what we'd be trying to find, because that's where theta is 90 degrees, pi over 2 radians. dy dx turns out to equal the ratio of dy d theta divided by dx d theta. That can be proved with the chain rule, though the thing you would initially prove with the chain rule is that the product of these two things is that thing, which would be true even if this thing is 0. In this form, this is only true if dx d theta is non-zero. Intuitively, if you pretend these things are fractions again, the d thetas would cancel and you'd be left with dy dx. And again, that pretending that those are fractions is technically not rigorous math in the way we teach calculus, at least. It's hand-wavy math. You can think of it that way, if you do something called non-standard analysis with infinitesimals. But we're not going to think of it that way. We're just going to go ahead and get the answer here. So for the sake of time, you'd plug this into here in the numerator. That's where this one goes. That's the dy d theta. And the dx d theta you'd plug in to the denominator. And that would be your answer for C. For D, we're trying to find the equation again of this line here, this tangent line. So we need its slope. We know a point in rectangular coordinates, x and y. X equals 0, y equals 2. We need the slope. Theta is pi over 2. I need to plug that value of theta into this fraction here. Plug it in here, divide by what I get when I plug in there. Sine pi over 2 is 1. Cos pi over 2 is 0. So what will that give me? For the numerator, look here. Cos pi over 2 is 0. That's 0. That's 0. Sine pi over 2 is 1. 1 squared is 1. I get a 1 on the top. And on the bottom, I plug pi over 2 into this. This is 0 because cos pi over 2 is 0. Negative 2 sine pi over 2 is negative 2 times 1 is negative 2. 1 divided by negative 2, which is negative 1/2. That's the slope. That's not the final answer, because I need to use the point x equals 0, y equals 2. Y minus 2 equals negative 1/2 x is one way to write it. Y equals negative 1/2 x plus 2 is another way to write it. The xy equation, this is a y here, xy equation of this tangent line to the polar curve. Okay? So you need to, again, remember some things. Okay, It is worthwhile, by the way, to memorize things to some degree. I mean, maybe you don't sit down with flashcards and memorize unless you need to. But when you got things in memory, it's so much better. You can access it much more easily. You can do more advanced problem solving if you do remember some things. If nothing else, it'll help you figure out what to look up in the first place if you do take some time to remember some things. All right, we got another Taylor series problem here, also called Maclaurin series again. Let f of x be the function natural log of x plus 1. Let's take a glance over the whole thing. Maybe we can be efficient here by doing more than one thing at a time here. Part A, find the fn of 0 for n equals 1 to 3, which means include n equals 2, where fn is the nth derivative of f, so I need to differentiate this. Part B, write the first 3 non-zero terms in the general term for the Taylor series centered at 0. Also could call that a Maclaurin series. Part C, just like before, we'll have to use the ratio test to determine the interval of convergence, which will help us find the radius of convergence. That's at least one way to do it. There actually is a direct formula for the radius itself, but I'll talk about thinking about the interval first. Show your reasoning, then part C, use the series in part B to integrate or to evaluate this integral with an error guaranteed to be less than 1 over 128. Yikes, how in the world are we going to do that without a calculator? Well, we will see that it can be done without a calculator. All right, so let's start by just taking the derivatives of this function. I'll put them up here. F prime is 1 over x plus 1, right? Times 1, because of the chain rule. The derivative of x plus 1 is 1. So this is the same as x plus 1 to the negative 1 power. F double prime, by writing it as negative 1 power there, I can avoid the quotient rule. I can just bring the negative 1 in front. Negative 1 plus x to the negative 2 power. Negative 1 minus 1 is negative 2. Times 1 from the chain rule, but again, multiplying by 1 doesn't change things, so I don't need to bother writing it. And we'll, I think, need f triple prime for sure as well. Bring down that negative 2, you get positive 2, 1 plus x to the negative 3. And actually, I know, based on knowledge about what we'll need to do in part D, related to the error term in a Taylor polynomial approximation, I will need the fourth derivative as well. The fourth derivative, 1, 2, 3, 4 of x, bring down the negative 3, get negative 6, 1 plus x to the negative 4 power. We will need that as well, though not for parts A or B. So now, part A, plug in 0. It's not requested in part A, but I will need it for part B. Let's compute f of 0 itself as well. F of 0 is natural log of 1 plus 0 is natural log of 1 is 0. And I technically do need to know that for part B, because it's going to be part of the Taylor series expansion. F prime of 0, plug in 0 here, you get 1. F double prime of 0, plug in 0 here, you get negative times 1 to the negative 2 is negative 1. F triple prime of 0, I plug 0 in here, 2 times 1 to the negative 3 is 2 times 1 is 2. Okay, I'm not going to worry about the fourth derivative until we get down to part D. These will help us write the first 3 non-zero terms. They're going to come from those things there for the Taylor series and also the general terms. So the Taylor series for this function, I'm not going to say it equals f of x yet, because there are only certain values of x where they're equal. The general form is f of 0 divided by 0 factorial, which is 1, by definition, to make formulas like this work out nice, times f prime of 0 divided by 1 factorial, which is 1, times x to the first power. This is essentially x to the 0 power here. Plus f double prime of 0 divided by 2 factorial, x squared, plus f triple prime of 0 divided by 3 factorial times x cubed, etc. This right here is 0 though, so that's not part of the first 3 non-zero terms. So the Taylor series is going to be p of x equals 0, which I won't write. F prime of 0 is 1, 1 times x is x. F double prime of 0, this is a 0 here, is negative 1. Again, negative 1 divided by 2 factorial is negative 1/2 times x squared. And then plus f triple prime of 0, which is 2 over 3 factorial, which is 6. 2 over 6 is 1/3. There are the first 3 non-zero terms. What's the general term? Say with an x to the n power. The signs alternate, plus, minus, plus, minus. You get a positive when the exponent is odd, and a negative when it's even. So this needs to be like an n plus 1, or maybe an n minus 1. That's an n plus 1 there that I wrote. Divide by n. That number, that exponent, needs to match with what I'm dividing by. Again, that's an n plus 1 there. Barely see that. And I don't claim initially that it equals natural log of x plus 1. And in fact, it doesn't equal it for all x. Only certain x it will end up equaling. And that's what we should start thinking about for part C to determine the radius of convergence. Now again, there is a direct formula for the radius of convergence. But I think it would be good to think about it the way we did before with the cosine problem. Think about this as your an. And once again, take the limit as n goes to infinity of the absolute value of an plus 1 divided by the absolute value of an. And once again, the absolute value signs make that negative 1 to the n power plus 1 power go away. I don't need to worry about it. N itself is positive. I don't need to worry about that. But x may not be positive. So I do need to keep an absolute value sign around x to the n, which is the same as the absolute value of x to the n. And with an plus 1, that exponent there, n, gets replaced with n plus 1. So I get n plus 1 here. I'm also dividing by n plus 1. And when you divide by the absolute value of an, you essentially flip this, except use n's instead of n plus 1's. When you think about this, you think of x as fixed, though it could be anything, in theory, ahead of time at least. This does simplify. This cancels with every one of those except for one factor of the absolute value of x. And as far as n is concerned, that's constant with respect to n. That can be factored out in front. And so you have the absolute value of x times the limit as n goes to infinity of n over n plus 1. And hey, that's a rational function of n. The degree at the top and the bottom are the same. They're both 1, first degree. So you look at the coefficients of the highest powers, they're both 1. Their ratio is 1 over 1 is 1, is the limit. That's intuitive justification that you should have learned. If you thought of n as a continuous variable, you could also verify that with L'Hopital's rule. So you get the absolute value of x. What does that tell you? That tells you for sure you're going to get convergence of this series, not necessarily to that function, but of the series converging, if the absolute value of x is less than 1, which means x itself is between negative 1 and positive 1. For sure you'll get convergence for those values of x. For sure you'll get divergence when the absolute value of x is bigger than 1, meaning x itself is either bigger than 1 or less than negative 1. Where it's unclear is at the endpoints, when x is plus or minus 1. That's unclear. As far as the radius of convergence goes, though, you don't need to worry about the endpoints. Our interval here is centered at 0, right endpoint of 1, left endpoint of negative 1. If you imagine this as being kind of like a degenerate circle, and actually if you go into the complex plane, it does become a circle, or disk. Its radius is the distance between the center and either endpoint, which is 1. That distance right there and this distance right there, those are both equal to the radius of convergence, which is 1. I mean these line segments here, those lengths. So r equals 1. That's part C, and your reasoning would be like this, and you'd probably want to mention the ratio test. To know it converges definitely when the absolute value of x is less than 1, which means if you think about it with a picture, that means r is 1. R is what this quantity is here. If it were 2, then r would be 2. As far as the interval of convergence goes, you're not asked about that, but if x were negative 1, you'd have negative 1, minus a half, minus a third, minus a fourth, minus a fifth, etc. It's the opposite of the harmonic series, which is known to diverge. So negative 1 is out, which makes sense also with this function. ln of 0 is undefined. Replace x with negative 1, you get ln of 0, which is undefined. When x is positive 1, this actually converges. You get 1 minus a half plus a third minus a fourth plus a fifth minus a sixth. It's called the alternating harmonic series. By the alternating series test, that does converge. The interval of convergence includes the right endpoint but not the left endpoint, but we're not asked that anyway. All right, on to part D. How in the world can we possibly do part D without a calculator? use the series from part B, this thing, to evaluate this integral to within an error guaranteed to be no greater than, in other words, less than, 1 over 128, which is that number as a decimal. They're not trying to trick you. You do want to use the first 3 non-zero terms, not the general term. The integral of f from close to where x is close to 0, 0 to 0.5 in this case, should be close to the integral of this when x goes from 0 to 0.5. That's the intuitive idea behind the approximation. Being sure of the error, though, takes more. But the approximation is that that integral is approximately the integral from 0 to 0.5, I'll just write it as a 1/2, of this function. Trying to save a little time here. Integrate that, you get, integrate x, you get 1/2 x squared. Integrate minus 1/2 x squared, you get minus 1/6 x cubed. Integrate plus 1/3 x to the third, you get 1/12 x to the fourth. This is going to get evaluated from 0 to 1/2. And the answer to that will be what you get when you plug in 1/2. No calculator, is that doable? Yeah, but you've got to be halfway decent at arithmetic. Let's see, put it up here. Plug in 1/2, you get 1/2 times 1/2 squared is 1/2 to the third, or 1 over 2 cubed is 1/8. 1/2 cubed is 1/8 times negative 1/6 is minus 1/48. This is a 1/8. Let me go ahead and change this to an 8. Plug in 1/2 here, you get 1/12 times 1/16 is 12 times 16 is 192. And then you'd want to get a common denominator of 192. 8 goes into 192 24 times. 48 goes into 192 4 times. 21 over 192 is your approximation. That can be reduced to 7 over, what would be, 64? 7/64 over 64 is your fractional approximation to this integral. As a decimal, we won't bother doing it. It would be a little bit bigger than 0.1. But how do you know for sure that it's no greater than? And if they're putting it in there, I mean, maybe they do want an explanation. That's not clear, actually, but maybe they do want an explanation. So let's think about an explanation. For knowing that the error in absolute value, they didn't put absolute error here, but they meant it. The absolute error, which is the absolute value of the integral of f itself minus the integral of that third degree Taylor polynomial, which I'll write as P3x. Little theory here, that's the same as the absolute value of the integral from 0 to 0.5 of f of x minus P3 of x. That's called the remainder that you get in approximating the function ln of x plus 1 with its third degree Taylor polynomial. This is a 0.5 here, it's not 0.6. And this, just telling you right now, and if you've done a BC calculus, you probably should have heard this, is less than or equal to the integral of the absolute value of that remainder, that error. It's really a sort of a, kind of like the triangle inequality, when you have the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. This is analogous to that, where integration is kind of acting like the adding. Well, now there's a theoretical fact to know. That this remainder, this absolute remainder or error, is less than or equal to m, to say what m is, divided by 4 factorial, why 4 factorial, Well, n is 3. It's a third degree Taylor polynomial. In the formula for this error, you get an n plus 1 quantity factorial times the absolute value of x to the n plus 1 power as well. And I could get rid of the absolute value signs there because x to the fourth is never negative. I could actually do the integral, though I don't have to. But what is m? M is the maximum of the absolute value of the fourth derivative in this case over the interval. X goes between 0 and 0.5. That's why I need that fourth derivative. Negative 6 times 1 plus x to the negative 4. In absolute value, I could get rid of the negative sign. And if you think about that function, positive 6 times 1 plus x to the negative 4, that's going to go down as x increases from 0 to some positive number, including to positive 0.5. The absolute value of this is largest when x is 0, and its value is 6 there. So you can replace this m with a 6. 4 factorial is 24. 6 divided by 24 is 1/4. And again, I could do the integral, but I think the point of the problem was actually not to do the integral, if you're thinking what I'm thinking here, but instead to replace the absolute value of x by its biggest value over the integral, which would be 1/2. Almost done. And that's a constant. In fact, it's 1 over 2 to the 6th power. 1 over 64. Over an interval that's a half unit long. This is less than or equal to 1 over 64 times 1/2 is 1 over 128. Yay. Would they really have you do this? I'm not completely ruling it out. I can't say for sure, so you should work at understanding it, but it certainly is a hard one, especially without a calculator. This one's pretty challenging too. Let f be the function whose domain is the interval from 0 to 9, like you see here. There's the domain from 0 to 9. 9 is right there. That's f. The graph of f is shown below. Consider the function h defined by this formula. H of x is an integral of f, but not from 0 to x, instead from 0 to x squared. Oh. Doesn't sound so pleasant. But it can be done. Certainly for any fixed value of x in the domain of h, which is going to be related to the domain of f, you can do the integral and get a number, theoretically at least. Part A, show that h is an even function. That's the easiest part. To be even means that if you replace x with negative x, that you really get the same thing as if you just keep it as an x to begin with. And that's easy because negative x quantity squared is the same as x squared. So it's easy to show h is even. What's the domain of h? The domain of f is 0 to 9. The formula for h does integrals from 0 to x squared. The only thing that works for x squared that is going to be related to this graph is when x squared is between 0 and 9. X squared is between 0 and 9. So what about x itself? Think carefully. That means x itself is between -3 and +3. And if we ultimately graph h over its domain, the fact that it's even means we can graph it to the right of the vertical axis and then reflect that to get the graph on the left side of the vertical axis. That'll be helpful in doing part E. But the domain is 0 to -3 to +3, because those are the values of x for which x squared is between 0 and 9. Think about it. Find h prime of 2, that's part C. Well, let's first find h prime of x. How? What? How can we differentiate this? Fundamental theorem of calculus. Not the one where you use it to evaluate integrals, but rather the one that the part where you use it to construct antiderivatives. If that were just an x there, instead of an x squared, the answer would be f of x. But it's not an x there, it's an x squared. So I really need the chain rule. If I let g of x be the integral of f from 0 to x instead of x squared, then h of x would really be a composition of two functions, g of x with, say, k of x, where k of x is x squared. H of x would be g of k of x. The chain rule says take the derivative of the outside function, which would be g prime. G would be the outside function in the composition of g with k. This is going to be g of k of x. The outside function is g. Take its derivative, plug in the inside function, k of x, multiply times the derivative of the inside function, k prime of x. The fundamental theorem of calculus tells you what g prime is. G prime of x is f of x, not f of t. You're thinking of x as being the number that you happen to be thinking about here. Ultimately, x is going to be 2. So I get here f of k of x, because f is g prime. More precisely, f of x is g prime of x. So if I replace x with k of x there, I've got to replace it here. Times k prime is 2x. So we get, and k of x is x squared. This is 2x times f of x squared. That's h prime of x, and therefore h prime of 2 is 2 times 2 times f of 2 squared. 4 times, what's f of 4? It's 0. 4 times 0, the answer is 0 for part C. But it's good to know this as well first, before you think about plugging a number in. So h prime of 2 is 0. Part D, give all values of x for which h of x is a maximum. Show the analysis that leads to your conclusion. So show your work. You really should show your work otherwise as well. So we need to figure out how to maximize h. How do you maximize a function? Take its derivative, set it equal to 0 to solve for the critical points, and then test those critical points. See if any give you a maximum. It doesn't say whether it's local or global. It will end up being global and local. X equals 0 is a critical point, as well as x equals 2, because h prime of 2 is 0. And yeah, when you replace x with 0, you get 0 there too. And h prime of -2, it turns out, would be a critical point, because -2 quantity squared is 4, and f of 4 is 0. There's 3 critical points. There's 3 places where this function, this derivative is 0. X equals 0, plus or minus 2. The plus or minus 2 works because f of 4 is 0. The f of 4 here was 0. That's why those two work. 3 critical points, plus or minus 2 and 0. Which of those gives a maximum? Maybe we should do part E to help us figure out which gives us a maximum. You can certainly approach part E intuitively this way. Excuse me, I meant to say approach part D intuitively by thinking about graphing h in part E first. You also could use the first or second derivative tests, though it gets kind of tricky. It's probably best to just graph h. Let's do that here. And this graph is a bit tricky. Remember the domain of h, -3 to 3. Remember, h is even. So graph it to the right of the vertical axis first, then reflect to get the part of the graph to the left of the vertical axis. Remember that h has this formula. Integrate f, not from 0 to x, but 0 to x squared. So if x squared happens to be between 0 and 4, and if I'm only thinking about positive values of x, that means x itself is between 0 and 2. Then this is the area under the graph from 0 to x squared, wherever x squared happens to be. If x squared is about 2.7, then x itself would be 1.6 or something. It would be the area under the graph. But if x squared is over here, then it's this area minus this area by the area interpretation and integration. The area increases as x squared goes from 0 to 4, meaning as x goes from 0 to 2. And it's got to increase fairly slowly at first, and then a bit more rapidly, because this graph is increasing. Has a maximum near 1.5. That's going to be where your inflection point is on this graph, and then it'll have a maximum, it looks like, at 2 before it starts going down again. Why does it start going down? Because now you're at values of x squared where it's over here, and the areas above the graph and it's below the axis contribute negatively to the integral. And in fact, if you think about it, it's going to go down pretty rapidly. Once you hit x equals 3, which means x squared is 9, it's this area minus this whole area, which would be negative because that area is bigger than that one in absolute value. So it's got to go down pretty rapidly, actually, to negative values, something like this. And now reflect this across the vertical axis, and the reflection over here is going to look something about like this. Something about like that. And so therefore you have maxima at plus or minus 2. And they would be equal to each other. The answer here is x equals plus or minus 2. And the heights of those, the maximum values would be this area, whatever that area is, and you could approximate it. And there is part E, essentially graphing h over its domain. All right, pretty tricky. Hanging with me here, or maybe you jumped into the video in the middle? I do refer back to the previous problem sometimes, so it's good to sometimes not just jump in the middle. Just a couple more problems. Oh, looks like another Taylor series, power series, which would be a Taylor series here, but we're going to use other techniques. More integrals. This looks hard again. It's actually not quite as hard as that other one from a couple problems ago. But you do need to know your fundamental facts, including the formula for the sum of a general geometric series. What I'm hinting at is when you see expressions like this, you should try to write them as something over 1 minus something. A over 1 minus r is the common letters to use. Because that'll equal a plus ar squared plus ar cubed, etc. An infinite geometric series it's called, as long as the absolute value of r is less than 1. So if I can rewrite that function in this form, where a and r could depend on x, I could use that formula, and that's a memorized formula. The key thing is to try to get a 1 in place of the 4, and that can be done by factoring a 4 out. That's one key thing. And having a 1/4 on the top for a. But how do you get a minus sign in there? Well, with a little trickery. Do that. Right, that works. 2 minus signs make a plus. You could check it by distributing the 4 back through. And yeah, now A is 1/4, and R is negative x cubed over 4, x squared over 4, which you could also write as, if you wanted to, negative x over 2 quantity squared, if you wanted to. And that is in a sense good, because the absolute value of that will be less than 1 when the absolute value of x is less than 2. So it is good to write it that way. This is the R here. The absolute value of that is less than 1 if and only if the absolute value of x itself is less than 2. The squaring doesn't matter because 1 squared is 1. So that's the radius of convergence. That's the answer to B. R equals 2. This converges when x is between -2 and +2. It's centered on 0. The distance between the center and either endpoint is 2. As far as part A goes, I want to use this formula. I don't have to take derivatives. This is good. A is 1/4, so I get 1/4. And after the first 4 non-zero terms in the general terms, so I get 1/4. A times R is going to be 1/4 times this thing. I guess I'll go back to that form of it. So I get a minus sign. 1/4 times 1/4 is 1/16 x squared. That's A times R. R includes a negative sign. Then A times R squared. We'll get a plus sign. 1/4 times this thing squared. The negative sign there will go away. 1/4 squared is 1/16. 1/16 times 1/4 is 1/64. And we'll have an x squared. Squared is x to the 4th. And minus 1/4 times this thing cubed. And the minus sign will be there because we're cubing it. And we have a negative sign there. 1/4 cubed is 1/64 times another 4th is 1/256 x to the 6th. The general term, if we think of the x power as being 2n, we kept multiplying by a 4th, and we also have a -1 to a certain power here because the signs alternate. When n is 0, it's a positive. When n is 1, think of 2 as 2 times 1. It's negative. When n is 2, think of 4 as 2 times 2, it's positive. So positive when n is even, negative when n is odd, and nth power will do there. We kept multiplying by 1/4 different powers of 2. So probably something like this will work. Here n was 0 in this case, and we had a 1/4. Here n was 1, and we got a 1/16. Here n was 2, and we got a 1/64. I think it's going to be 2n here. Double check that. Like when n is 3, 2n is 6. N is 3 there, you get 2 to the 6th power, which is 64 times 4 is 256. Yes, this works. I could also think of 4 as 2 squared and combine those. All right. And the radius of convergence is 2. Now on to part C. Do that integral. So we got to integrate this thing term by term, except I replace x with t. It's just a dummy variable. It doesn't really matter what you call it. In in the end, when we integrate these things, thinking of t as the variable, we'll ultimately go from 0 to x, so we'll replace t with x back again. And when we replace t with 0, we'll get 0. Ultimately, we can effectively just integrate this as if it's an indefinite integral. 1/4 x minus, look at this one, x cubed. 16 times 3 is 48. This one, x to the 5th, 5 times 64 is 320. Minus x to the 7th, 7 times 256. Let's see, 8 times 256 is 2048. 7 times 256 would be then 1792, I think. Check my work, I think that's right. And so that is part C. D is the hardest part as far as conceptually speaking. Use your answer to part C to figure out that this is true. What? Where in the world does that come from? That's the trickiest part. The key to seeing it is to realize that this function equals this, and so therefore the integral of this equals this. This function is what's in blue. The integral of this function is what's in red. But the integral of that function done another way would involve the inverse tangent function, arctangent. What we've got here in red should equal antiderivative of that, which you could also think of this way. Maybe combine those two minus signs to get a plus sign. Something involving arctangent of x over 2. Well, what's the coefficient? We want its derivative to include the 1/4 there, so it seems to me it should be a 1/2 arctangent of x over 2. You can double check that by differentiation and simplifying. Oh, let's see the chain rule. I'm pretty sure that's right. I guess we'll see if it's right in part D. How do you use that? Plug in a special value of x to make this match with that and this match with that. What would make 1/4 x match with 1/2 if x were 2? What would make 1/48 x cubed match with 1/6 if x were 2? 8 over 48 is 1/6. This is going to match that when x is 2. What about this when x is 2? Plug in x equals 2, you get 1/2 times arctangent of 1. That's what I'm trying to write there, 1/2 times arctangent of 1, because 2 over 2 is 1. Arctangent of 1 is pi over 4. Hey, 1/2 times pi over 4 is pi over 8. That's supposed to be a pi, sorry. And yeah, plugging in 2 here gives you that. So you get part D by replacing x with 2, also realizing that the integral of that is this 1/2 arctangent of x over 2, plus c for a general antiderivative, but the c is 0. Whew. We're on to our last problem. Yay. And I am ready for lunch. I don't know about you, but I'm really hungry. All right, one more problem here. Problem 8, yeah. Had to make the last one a tough one, huh? It's not as tough as it looks, but it's still a bit unpleasant. Ever seen such curve? Y squared minus y plus e to the x equals cos x. The part of that curve near this point, x equals 0, y equals 1, defines y implicitly as a function of x, which means that little piece of the graph passes the vertical line test, is what it means. Could you explicitly solve for y as a function of x? You actually could here. You could use the quadratic formula. after subtracting cos x from both sides and thinking of x as fixed, you could write this for y as a function of x. Does this point, is it on the curve? When x is 0 and y is 1, is this equation true? Well, e to the 0 is 1, cos 0 is 1, so these are both 1. And then 1 squared minus 1 is 0. You get ultimately 1 equals 1. It does satisfy the equation. It is on the curve. It's implicit differentiation. You need to think of y as a function of x. And differentiate both sides with respect to x. And the derivative of y squared with respect to x is not 0. It's not 2y either. What is it? It's 2y dy dx. What? Where in the world did that come from? Well, hopefully your teacher taught you about this. You should have. Y is a function of x. That's analogous to differentiating f of x quantity squared, where f is some unknown function. And you need the chain rule for that. You bring down the 2, then multiply times the derivative of the inside function. This expression right here is the exact same thing as this one right there, just different notation. Because y is a function of x. We're not finding the formula for that function, but there is some function. If you graph this equation here, this point, just a little piece of it, not the entire curve, it will pass the vertical line test. Actually, the entire curve, I checked it with my technology, fails the vertical line test, which makes sense because if you use the quadratic formula here, you get plus or minus. And it's a pretty cool little curve. It actually looks like a sideways egg. Try it. If you got technology to do that. It looks like a sideways egg. Not a circle, not an ellipse, but an egg. What's the derivative of negative y with respect to x? Not 0, not 1, it's dy dx. Or f prime of x. What's the derivative of e to the x with respect to x? It's e to the x. What's the derivative of cosine of x with respect to x? It's negative sine x. There's what happens if we differentiate both sides with respect to x, assuming the equation defines y implicitly as opposed to explicitly as a function of x. There's no explicit formula for y as a function of x, here at least. But there is one in theory, and in practice you could even find it. Now what's left to finish part A is just to solve for dy dx algebraically. Subtract e to the x from both sides to cancel it on the left. Factor out of dy dx out of those two terms and divide both sides by 2y minus 1. If you do that and then cancel the negative signs, you'll get e to the x plus sine x divided not over 2y minus 1, but 1 minus 2y. So that's the answer to part A. Part B, find the value of y where the tangent is vertical, meaning undefined slope, infinite slope. In general, that can be a pretty tricky question. You are looking for where this fraction would be dividing by 0. Though that can be tricky because what if the top is 0 at the same point? In this case, you don't have to worry about it. The top just depends on x for one thing. So you can just focus on where the bottom is 0, and that's going to be 0 when y is 1/2. So along the horizontal line at y equals 1/2, that egg shape that this graph has will have a vertical tangent. The egg, watch my hand here, looks about like this. Vertical tangents along the line y equals 1/2 when they cross, when the two graphs cross. Part C, find an equation of the line tangent at point 0, 1. So I got to find the slope there, use the derivative. dy dx. You evaluate it at the point 0, 1. X is 0, y is 1. Is not as hard as it looks. E to the 0 is 1. Sine of 0 is 0. 1 minus 2 times 1 is 1 minus 2 is negative 1. You get 1 over negative 1 for the slope. So the tangent line at that point is going to have equation y minus 1 equals negative 1 times x, which is equivalent to y equals negative x plus 1. Ah. There we go. That's the tangent line at that point. Going to skip part D for the moment. Let's do part E. Use the tangent line approximation from part C to estimate the value of y for the point on the curve near this point, but slightly changed. Let x be 0.25 instead of 0. All you have to do is just use the tangent line. That's all you have to do. For part C, y is approximately negative 0.25 plus 1, which is 0.75, when x is 0.25. Is it exact? No. That would be a linear approximation to a curve. It's not going to be exactly right. On part D, we're trying to estimate whether it's too big or too small. And for that, we need part D as well. Ugh. What do I do for part D? There's dy dx. I guess I need to differentiate both sides with respect to x to find second derivative? Yeah. But wait a minute, the right side involves a y. How do you do that? Well, remember, y is a function of x. I could replace that y with an f of x. I still need the quotient rule here. I always remember it as low function. D high means times the derivative of the high function, derivative of the top, e to the x plus sine of x. Its derivative is e to the x plus cos x. Minus, that's low d high, minus high, the top function. D low means the derivative, d for derivative, of the low function. With respect to x, the answer is not 0, it's not negative 2. It's negative 2 dy dx. Divided by the square of what's below means y, 1 minus 2y quantity squared. Ugh. Yikes. This dot does need to be there to emphasize your multiplying here. I could bring the negative 2 in front and make a plus 2 there. And what do? Well, I could continue simplifying this. I could, for example, replace dy dx with that thing. And it's not terrible. You can do it. You also just can plug numbers in now. And it's not as bad as it looks. Plug in x equals 0, y equals 1. And we know dy dx there is negative 1. That can be plugged in to there. What will we get? X is 0, y is 1. X is 0, y is 1. We get negative 1 there. X is 0, 1 plus 1 there. So negative 2. All that matters ultimately is whether this is positive or negative, which means the bottom doesn't really matter. It's the sign of the top that matters. Minus, plug in 0 there, you get 1 plus 0 is 1. Plug in negative 2 and negative 1 there, you get positive 2. 1 times positive 2 is positive 2, but we're subtracting it. If I have not made any mistakes, that would simplify to negative 4, which is negative. Meaning, the graph is concave down. I did say it's an egg shape. Turns out to be about this shape. And this is y equals 1/2 here. Yeah, where the curve was vertical. And the point in question turns out to be right around here somewhere. That's the 0.01. And you can see that this little piece of the graph, which is all you need to consider, does pass the road to line test. Its tangent line is above it because the graph is concave down there because the second derivative is negative. The tangent line being above the curve means the y coordinate here is too large. That's the answer. Because the tangent line is above the curve, because the curve is concave down there. Wow. AP Calculus BC is tough. But if you've worked at it hard enough, for long enough, and close enough to the exam, I hope with the help of my video and other videos that you can succeed. Thanks for watching.